I'll tell you what that means. So the butterfly, let's start with the butterfly effect. Other than being a really terrible Aston Kutcher film from the turn of the century, it's this idea that Edward Lorenz is one of the fathers of chaos, and he invented to a great degree chaos theory when he did this work on the atmosphere, and he found that very small effects got amplified. He said one flap of a butterfly's wings in the Indian Ocean can cause a hurricane in Kent a week later. I didn't say Kent, I think he was talking about somewhere else, but I quite like the idea of a hurricane ravaging Kent. And my wife would probably disagree with that. And this pattern here, this is called the Lorenz attractor, which forms a sort of butterfly pattern, which is a really nice, kind of weird symmetrical coincidence about with the sort of theory of chaos and the butterfly flapping its wings. So what does this mean? Why are all these butterflies flapping their wings and they're causing tornadoes? Can we just catch them and stop all of these extreme weather events swooping across the world? Well, it's not really to do with these individual butterflies. It's to do with the effects of very small changes on the system at some point in the future. And to understand what that's about, you have to go back to a view of the world that's sort of Victorian's, deterministic view of the world. It's a mechanistic view of the world. The world is this finely oiled machine. And that means mathematically you can make equations which, if you know the current state of the world, you can predict the future. And I liken this to this domino rally. You set up all the dominoes. Obviously you can't set up the world, but you know where all the dominoes are. And not only when you knock over that first domino, not only do you know that all those dominoes are going to fall over, you know when they're going to fall over and how quickly, and you can predict that into the future. You can go into the future, into your huge domino rally, so you know when that face of Marilyn Monroe is going to appear, and when the rocket's going to launch and the balloon's going to fall over, and so on. So you've got a perfect prediction of the world in the future. That's this Victorian deterministic view of the world. No, I don't think this video runs, unfortunately. No, it doesn't. It's a static image. This is it's worth looking at. This is a domino rally done with I think it's packets of empty mashed potato that some some school in Canada did, and they built this whole domino rally, and there's people and whatever. If you look at this video online, what you'll see is that the kid starts off the rally and it kind of stops after a bit, and so he has to run around the side and do something to knock over some more, and then on the other side, well, it stops over there on the left, and he has to run back around and start again. And what it goes to show is really the world is more complex, more complicated, let's say, in real life than it is in our simple mechanistic understanding of the universe. So you can kind of imagine a circumstance where whether all of these fall over, or when they fall over, or if there's a delay, or if you have to go around and kick some over, that's determined by something that happens at the beginning. How hard you flip that first one. You know, whether you get it at quite the right angle, maybe it falls over to the side of it, and that doesn't give you quite enough speed. And pretty soon, just that little difference, that flick of the initial mashed potato box has manifested itself in Marilyn Monroe's face not appearing, the rocket not launching, or the balloon going up at slightly the wrong speed, and there's some sort of domino catastrophe going on. So there's little changes, there's little things at the beginning influences the overall behaviour of the system in a way that you can't necessarily predict. There's tiny changes get amplified, so that if you go far enough away from the initial event, you can't predict what's going to happen. Even though that's a deterministic system, it's determined by the laws of physics, you can't predict it, because any errors in your initial measurement will get amplified and blown up. And that's the idea that Edward Lorenz was talking about, is that you can measure atmospheric pressure or humidity, but if you get it just a little bit wrong, you go a few days into the future, as we know, weather becomes really, really unpredictable. So if you think about chaos theory, which is not the same thing as complexity, but chaos theory is amplification of tiny changes. The triumph of determinism, because it's a deterministic system, it's determined by what happens at the beginning, but you can't predict it, it's too difficult, it's too complicated. And in a sense, complexity is the same thing, but with lots and lots of butterflies. So now imagine, well, in fact, you don't have to imagine it, this is the case. You've got butterflies all over the world. If that tiny amount of inaccuracy is important, surely that happens whenever there's a butterfly flapping its wings. Surely that contributes to this complicated picture we've got of the world. And yes, it does. And if you think about it, not butterflies but human beings, think about a social system, think about international politics or trade, or think about the way a city works, or the way a transport system works. You've got 7 billion butterflies all flapping their wings, and all of those elements contribute to the system. It would be like if we had loads of people running around knocking the dominoes at different points. Pretty soon it gets difficult to predict, but also it's important what each of those individuals does. You can't just look at the one person starting off the rally if there's other people running around knocking things over at random. Okay, so that's kind of what complexity is. So what's the difference between complex and complicated? Well, this is an example of something that's complicated, right? There's loads of, I don't know how an engine works, I don't own a car, literally no idea. But there's lots of bits in an engine, right? But the output of what that engine does is simple. As far as I'm concerned, there's a non-car owner. That makes a wheel turn. It doesn't blow up. That's it. Yeah? So you've got this really complicated system where there's different gaskets and there's bits of metal and rubber and steel and and it does something really simple in the end. So you've got lots of complicated interacting parts being designed for a simple purpose. Complex systems have the opposite facet. They're not necessarily designed for a purpose, so this gets into sort of metaphysical territory. But they're simple elements usually that combine together to make complicated behaviour. So the individual bits are quite simple, like a water molecule, it's just this sort of V-shaped molecule floating around. But when it gets together with other water molecules, you get this incredible complexity and diversity of form that you couldn't necessarily predict by just thinking on this V-shaped molecule. And there's this sort of, I like to use this sort of existential idea that existence precedes essence. With an engine, you decide what you want it to do, and then you make it. Whereas with complex systems, as with human beings, they exist, and then they somehow determine some straight shape or form or structure, which goes beyond their physical existence, and that happens afterwards. That's what we determine in our lives. So, the kind of, we used to dealing with, in science, we used to dealing with systems with lots of bits, lots of components and things which fit together, but they normally are systems which are linear in some way, and the events are unconnected, and a small change to an individual element leads to small changes in the whole system. So, an example might be a roulette wheel where you spin it again and again and again, and you look at the results. And you can use statistics to say, is there a bias to this roulette wheel? Because the events are sequential, they're unconnected. Whether I get a red 36 doesn't influence whether I get a black 11 in the next game. There's no step-to-step correlation. Whereas in a complex system, these are elements, whether they're human beings, whether they're ants, whether they're biological entities or chemical entities or some other kind of entity, they interact with one another, and that interaction makes a much more difficult to unpick system than if they were just acting in isolation and you were just measuring, the height of people. I mean, that's an example of something that the heights don't necessarily influence one another. But if you were looking at, an economic system, suddenly those people influence one another a great deal. So, how do you understand these systems? It's hard. You have to think about things in different ways. You can look at certain kinds of maths, which come out of chaos theory, to look at the system as a whole, and whether it's stable or unstable, whether it tends to a certain kind of agglomeration, kind of clumping effect, or equality or inequality, these sorts of things. You can build computer models to try and simulate the way that individual entities behave. And again, that could be people or cars or ants or flocks of birds. Again, you have to simplify the way that these systems behave, these individuals behave. And you can start to look at network theory, which is a set of ideas around how these things connect to one another. Actually, this is a graph of my university structure, so it's just a hierarchical graph showing all of the departments and all of the faculties and all of the schools within UCL. But you can do something more clever than that if you want to understand social systems, to understand transport systems and spatial systems and cities and things like that. So how complex is too complex? So the question there is, how can we understand these really complicated systems? Human beings as individuals are complicated. You put them together, they get very, very complex indeed. I like to think that 150 years ago, people were sitting around saying, how are we ever going to understand a jar of gas? There are so many atoms in it, it's too complicated. But yet we found techniques to understand the statistical properties of a jar of gas. We can't say what an individual atom is doing, but we can understand what a jar of gas is doing. So can we do the same thing with social systems and complex systems? And the answer is, I hope, yes. Thank you. fantastic dance piece which follows on from this, which is inspired by those ideas of complexity, specifically complexity in the city. The way that all of our lives are sort of lived individually, but so many times we interact with other parts of the system and we influence others, even if only in very peripheral ways. And there are times when we move along in parallel, and there are times when we collide quite violently. And within these systems, there are certain agents of change that move through, and they enable these connections, and they forge and break these connections within these complex systems.